So, a short video about Cantor's diagonal argument as well as Cantor's theorem. Around about 1890, Cantor stated two arguments about infinite sets. The first is for sets like natural numbers or integers, and they are countable because you can represent them as a sequence. The second argument is for real numbers that shows you that this set is uncountable. So imagine you have an interval between 0 and 1, and you write down every number of this interval into a list like this one, and they can be written down randomly. Then you take a bijection, which means if you have a bijection, both sets have the same cardinality, and as we know, m is countable. The numbers of the interval 0 and 1 should be countable, but you can easily show that this list on the right is not complete because you can create a new number which is not on the list. So with the diagonalization, you change the numbers here. I just add 1, but you can do it as you want, but they have to differ at every position in the column. So 0 goes to 1, 2 goes to 3, and so on. And then you have a different number, which is not on the list. And of course you can add this number to the list, but with the same algorithm, you can create a new number which is not on the list. So because this process goes to infinity, it is not complete. The list is not complete. And because the list is not complete, it's not countable. So the interval between 0 and 1 is not countable. And because it's a subset of R, it holds for R that R is uncountable. So the same argumentation holds for Cantor's theorem. For any set S, its power set P has strictly greater cardinality. So you assume that both sets have the same cardinality. So there exists bijection. As before, you write down a sequence, for example, natural numbers to infinity, and have a bijection for every position to a subset, like 2 times n or n of s. So f of x is the bijection. And you create another set, it's called T, or you can call it T, and it has the requirements that the elements have to be part of S, but are not part of the function of the bijection. So you look, okay, is 1 part of 2 times n? No, it's not, so you have your first element. 2 is part of the natural numbers, so you leave it. 3 is not even, so you write it down, same for 4 and 5, and this goes to infinity. So because T is a subset of S, it has to be part of the power set by definition. So at the nth position, you have 2 cases. The first one, n, is an element of T. So if n is an element of T, it means that n is no part of the function which is defined by T. But this means, no element of f of x. So this means it's no element of T because it's not in a function right here. And you have the second case. You assume it's n is not part of T, And this means it has to be part of f of x. So it is in the list and is therefore a part of t, as n is a part of t, an element of t. So as you can see, it's a contradiction. It's not working, and our assumption has to be wrong. Our assumption was that there is a bijection between S and P, but there is no. So it means if there's no bijection, it can be a surjection or injection. But we know the function has to be at least an injection, because you can map, for example, the 1 to the set of 1, or the 2 to the set of 2, and therefore you know that at least the power set has at least the cardinality of n. So the cardinality s, which means the natural numbers right here, is strictly smaller than the cardinality of its power set S. So it is shown that the Cantor's theorem holds, and if you have some questions about it, I hope the video makes it clear, but if you have, just write it down in the comments and I try to answer. And yeah, thank you for watching.